committee, but Fritz asked me to remind everybody to send, if you have pictures, or if you have anecdotes, or anything else from the history of PEPM, going all the way back to the mixed computation days, send them to the history committee. They're planning a history celebration. So it's called the 30-year plus. And that's definitely true, because 87, that's definitely at least 30 years. So they're planning a bigger celebration of the history of PEPM next year. Find the email address of Fritz or one of the other people on the committee and write to them. And otherwise, just participate in the history celebration next year. Okay, so after the welcome, I want to welcome Adam Chlipala, who is our invited speaker. So Adam, aside from being a famous professor at MIT, so let's see. So you were undergraduate at Carnegie Mellon, graduated in 2003. And then he went to Berkeley and studied with George Nekula and graduated in 2007. And actually, I remember a very nice dinner with you in San Francisco when George Nekula was general chair of POPL in 2008. So you must have just gone on to be postdoc at Harvard, or were on your way in 2008. So you were just en route to Harvard. Then he was postdoc at Harvard until something like 2011, I suppose. And then he has been professor at MIT ever since. So of course, Adam can prove anything in POC. He has a book about how to prove anything in POC. He has a startup company where I'm sure they're proving stuff in POC along the way, maybe not so much. But the thing is that aside from proving stuff, he likes to build software, and particularly web software. I'm a big fan of Web, which I think is the language for programming web stuff, and there are dependent types everywhere. And so it's just like, I feel like so lucky that we can have a PEPM where Adam is the first speaker, and he's going to talk about cryptographic code. So thank you.
it'd be great if we had a compiler where you can tell it which data structure you want, and then it does all the rest of the work producing your code, and the compiler is formally verified. What could be better than that? So that's what we set out to do. We built a library called that parameterizes over your choice of this data structure for big integers, and then it'll produce fast C code encoding other languages. Of course, the library itself is approved once and for all in Call. And if you zoom in on how the library is structured, the top level is a set of functional programs implementing different arithmetic algorithms. For some of them, like multiplication, there might be a few different variants where for different primes we want to make different variations. Those are all written and approved. And then we apply partial evaluations to specialize those to the choice of prime and data structure. So the result of this is a flatter functional program. No longer using higher order features, you can kind of squint at it and say, hey, it looks like a C program now. And then we make that official by applying some compiler optimization kind of techniques that will actually produce code in C or Rust or whatever by analyzing the flat functional programs that came out of the previous stage. And all these steps are either proved or proof generating. So they all compose together, showing correctness of the code that comes out. So let's look at an example of something that happens in each of those stages. But just think about multiplication in a bit more detail now. I'm choosing a similar modulus to the 127 minus 1 here, where we might naturally represent each number with 3 digits. So I'm showing the formula for reassembling the big number from those digits up here. So let's multiply S and T together. There are 3 terms in each of S and T, so we're naturally going to get 3 times 3 cross products, all the ways to multiply these terms together. So I assemble them all here. And then I orient them in a suggestive way where we have columns where the powers of 2 are very close together, if not equal. Because we're going to build our 5-digit result of this multiplication by matching up the digits with the columns of this picture. So here's the recipe for computing each of those 5 digits as a function of the original digit that base. And then the only problem we have left is this is 5 digits. I wanted 3 digits in the output. So if I look carefully at this formula for reassembling the big number, that's the result of multiplication, and I've grouped some terms together, so I have a 2 to the 127 factor in one place. That is congruent to 1 in this prime modulus, so I can sort of cross it out, and then take these 2 terms, U3 and U4, and just redistribute them into other positions, and now this is our final result, the formula for creating a 3-digit version of the output of this multiplication. So you might be able to imagine at this point, you could write a program that generalizes this algorithm across different base systems of representations. And if you're used to using a proof system, at least, you might imagine you can prove it, like what we did for this and a suite of other algorithms that matters for these cryptographic systems in practice. Then we need to specialize them to particular problems and outcomes, a program that has dropped the overhead of generality. So in an algorithm like that, we can view as having compile time arguments, the choice of data structure, the digit bit widths, and runtime arguments, the actual digit values. So we want to specialize digit bit widths and then apply reduction or algebraic simplification to get out a version that is now streamlined and only handles this particular data structure. This turns out to work really well in Call, which is a great platform for symbolic computation in general. The specialized step is just partially applying a curry function. It's like totally free. And reduce is just the workhorse operation of interactive proof assistance, algebraic reduction of functional programs. This is built in at the lowest, most fundamental levels of Call. Doesn't mean it's easy to get it to run quickly, by the way, but I'll come back to that. Conceptually, at least, it's straightforward to set up this specialization pipeline. Here's an example of how this looks at the top level. This first line of Call code, defining the function W, is expressing our data structure. It maps a natural number for the position in the sequence to the power of 2, that is the weight of the digit that appears at that sequence position. And then I can state a proof goal to find the correct implementation of multiplication. Takes, in this case, 2 10 tuples of mathematical integers, f and g, and needs to produce a new 10 tuple, fg, and then this formula here just expresses the correctness of multiplication using the function eval that converts one of our multi-digit representations back into a big number. So we're going to use Call tactics to find the correct multiplication code at the same time as its proof. So by construction will be a correct function. And I'm going to elide the exact details of the tactics we invoked there, but the result that comes out is a perfectly readable formula like this one. Here's our tuple. Each of the positions has a big sum in it with some scary magic numbers, 38s, 19s, and so forth. We can be glad we didn't have to write this, and by construction we know it's giving the correct answer, so we don't have to worry about the details. So we're almost there. I want to get some C code out of this. And so let's look at a simpler example of expression. Imagine this was one of the digit formulas, some kind of expression with free variables standing for integers. I want to get a level code out of this. So first I'm going to reify it into a syntax tree, an AST type inside of conc. And I'm going to apply constant folding, maybe other classic compiler optimizations, shrink it down as much as possible. And then I want to flatten it. So I introduce names for all of the intermediate computations. We're getting very close to looking like assembly at this point, but what's still missing is our integers are unbounded mathematical integers. So we're going to do some abstract interpretation to infer bounds for the different integers. Let's assume we just knew that the inputs x and y of this algorithm are bounded like so. Then we can push that information through each of these lets. We deduce a bound for C, deduce a bound for D, and we look at those bounds and we see, okay, the lower bound is always above 2 to the 32, upper bound is below 2 to the 64, so I should really allocate a 64-bit register to each of these temporaries. And we can generate some C code like this. So all these steps, again, are either verified or proof generating. So the correctness arguments here will compose with the ones from the earlier stages as well.
So this point about greater than 0 means you use unsigned int, because you know you don't need the sign.
I think that might be below the abstraction level of my knowledge as the overseer rather than the coder here, but good question. All right, so this is how things basically work. Let me tell you how we ran experiments to test how good of a compiler this is, independently of the proof aspect. So we need to be able to quickly run many different test cases using different prime numbers and different hardware architecture targets. And we wrote a Python script that makes this look like a pretty standard automated command line compiler. It will look at a prime number written in this suggestive style of subtracting and adding different powers of 2, and then apply some heuristics of giving your hardware architecture target, makes a guess of actually a few different potential data structures. Then we're going to benchmark with all of them and keep the fastest one. This heuristic doesn't need to be trusted. If it makes bad suggestions, it can compromise performance, but not correctness. Then we needed enough inputs to test on. So the way we went about that is scraping a popular crypto mailing list, finding everything that looks like a prime number, and using that as an input. And so we found about 80 different prime numbers that were on this elliptic curve mailing list. And only a few of them turned out to be bad ideas that actually no one knows how to implement correctly, so maybe our compiler times out for those, but at least it's not going to give incorrect code. So then we automatically generated all of those, or we tried to generate all those prime numbers. This first experimental graph is about for running on a 64-bit x86 laptop. And we're comparing against the previous best generic implementation of big number modular arithmetic, which is the GNU multi-precision library, which is a very dynamic approach compared to ours. It's kind of making choices and allocating memory dynamically at runtime. And there's two variations, one with timing side channel security and one without. But regardless of which we compare against, even if we compare against the insecure version, the results from our compiler in the lower line here are significantly faster on this benchmark for running. X-axis is number of bits in the prime modules, y-axis is running time on some representative test case. We're often in the neighborhood of 5 to 10 times faster than what you got with GNU multi-precision library before. And of course, there were no proofs there. So it was like you're winning on all the axes, except I guess you need to be a formal methods expert to build this. Was that a question?
Yeah, and you're secure by design because it's straight line code and we're not doing anything dynamically. That's like examples.
All right. So the target language of the compiler by construction only admits side channel secure code. Yeah. Yes.
Do you use quadratic complexity for integer multiplication, or do you implement a sub-quadratic algorithm? doesn't make sense at these sizes.
I think that question's below my pay grade. I don't know. I didn't personally implement anything. That's the literal answer. But good question. We wind up with the same code that the experts were handwriting. So if you look up what's the state of practice in OpenSSL, the answer there applies here too. Okay, and of course, nice thing about compilers, same source code, many compilation targets, no problem. We also generated for a 32-bit ARM mobile phone and got pretty similar results for essentially all the same algorithms, or at least all the same functionality. Sometimes that heuristic that I mentioned might actually choose a different algorithm for such a different target as well. All right, so this is comparing against code that no one was using in practice for cryptography. This was just the easiest way to mimic the generality of our approach. What we really want to compare against is the code that was handwritten by experts. So here's P256, one of the most commonly used elliptic curves, say, on the web. And here's our results in the italic-headed rows here, where we reason two different C compilers to compile the C code we produce. In this case, and all the others, at least at the time of our original paper, we did produce the fastest known C code for all the elliptic curves. So here we're comparing against OpenSSL's platform-independent C code, which doesn't compare very well to OpenSSL's own platform-specific code, but at least we're able to beat it pretty well, especially using the ICC compiler from Intel. There are still handwritten assembly versions in OpenSSL that are a factor of 2 ahead of us here. I'll talk near the end of the presentation about closing that gap a bit. This is actually the hardest elliptic curve to implement efficiently. So the one I mentioned before, 2 to the 255 minus 19, the C code we produce is almost indistinguishable in performance from the best assembly code. So I kind of picked one of the toughest examples to highlight here. But at least there's no manual human effort required here to produce this code, and formally guaranteed to be correct. So this was enough to make the Chrome team decide that they'd rather use our version over something that they'd written by hand. So let me talk a bit about that adoption. We did have good success getting practitioners of cryptography to use this tool, and what are some of the reasons, as I reflect on this, that I think that worked? There's the maybe most obvious reason, general paranoia. Cryptographers are more worried about correctness of code than your typical software engineer is. Though there are other approaches to getting assurance in this domain that compete with ours, like there's a nice library called Hackle from the Project Everest team centered at Microsoft Research, which is not about a compiler that writes the code for you, but just verifying handwritten code. Get the same benefit in terms of trust there, except we're using a proof assistant, not an SMT-based verification tool, so we have a significantly smaller trusted code base. This is a subtlety that's hard to convey to practitioners of cryptography. So this probably isn't a reason why people would choose our tools over the competitors. But then there are real situations that I'll describe here that occurred in the Chrome security team where they were glad to adopt our tool. So they had sitting around a 64-bit C version of this elliptic curve P256 that I mentioned. Wouldn't you know it, whoever wrote it wasn't on the team anymore. No one understood it. They were really petrified of changing it. So they were able to get rid of that code and just run our compiler to produce an alternative for it. But even better, they never had a 32-bit version before. So once they started using the compiler, they could just produce their 32-bit C version, put that into production, and get significantly better performance for any target that needs to use the C version rather than the assembly version. So this is like a classic benefit of using compilers instead of writing assembly code. We're glad to be able to bring that to this domain where it's previously seemed performance prohibitive to use that kind of solution. There's also a counterintuitive example that came up where for another popular elliptic curve, the team had been maintaining a 64-bit assembly code file. Also, I'm not too confident what's really going on there and how to change it soundly. But they had an idea for a new high-level algorithm that required an interface change for their low-level arithmetic routines. So they were able to realize that idea by using our tooling to produce a new version of the same functionality with a slightly different interface. Now even in C code instead of assemblies, you'd expect some kind of built-in performance cost there. But it allowed them to use different high-level code for a new algorithm connected to it. And they actually got twice the speed compared to the old version of despite switching this from assembly to C. And of course, even stronger formal guarantees than before. So I think these scenarios can be pretty compelling, even for people who don't quite buy into the benefits of formal methods. So was formal methods important for adoption of this tool in practice? Maybe it was. Maybe we were at least able to build our compiler more quickly and efficiently by using formal proof to replace testing and other laborious activities, in which case, that's great. We showed that formal methods is truly helpful for improving productivity in industry. Or maybe formal methods wasn't central to why people wanted to use this. Maybe they just wanted a new kind of compiler. Maybe they just love partial evaluation and program manipulation. But then that's fine too. It means we were able to do formal verification of a truly production quality compiler using only cheap student labor. That seems like great evidence that formal methods is feasible. Okay, so I think I'm going to start going into a few of the more recent improvements to this tool chain, but I want to pause here and ask if there are any questions about the original formulation of things. Yes?
This is really nice and impressive. It's interesting that you're using reduce to try to flatten the program, the expression, because reduce is optimized for finding equivalent terms. Whereas if you're trying to calculate something, you want to get like maximal sharing of the expressions you So you do additional post-processing to get that, or is that somehow?
Well, we actually have to design, especially in the original project, I'm about to get into this here, we had to design the original functional programs so that this built-in reduction would work properly, including in dimensions like preserving sharing. And it was a pretty big pain in the butt. And the next part is going to show how we can not hurt as much there.
So you mentioned that one of the teams wanted to raise the level of abstraction of one of their assembly codes. So how did they go about it? Did they just contact you and they said, oh, here's our high-level idea, and you coded the algorithm in your library, or were they able to do it on their own? So I just want to figure out what is the process of adding new contracts to your
It's a gradual process of education. So all four of the student authors of this paper have worked at Google by now, helping get this tech transferred. But they did manage to teach a few other people who weren't formal methods experts how to think about this and just run a new command line compiler with slightly unusual argument convention. And some of these cases I talked about involved code that was generated without even consulting us. We put in some effort on usability and documentation of the compiler to the point where that's feasible.
Thanks.
Any other questions here?
I want to understand this thing about the speed just a little bit more. So whether you have these listings where it's like half a second or quarter second or something.
Yeah.
As a user of these systems like Google Chrome or something, where would I notice whether the speed of the start is two times faster or 2 times slower?
If you're going to notice, it'll be in the loading time of web pages.
Each time there's a load.
Every time you load a web page, there are many different TLS connections, and each one needs to run all the algorithms that we're generating.
So it could easily be like a latency of another second for loading the company.
Well, I'm not sure about that level of detail. I think that the practical payoff shows up more in Google servers, which also run this code, where maybe they can demonstrate some fraction of a percent improvement in power usage because of this. But also power on your mobile device could benefit significantly from optimization here at the level of probably less than a percent.
Thank you for your talk. And you mentioned that you will verify security property. I'm wondering what
I mentioned that
property.
we don't verify security properties, but other people do. And there's good work that connects these kind of proofs, but we didn't do it for our project yet.
I see, because there was a protocol verification for
Right.
it. I see. Okay, thank you.
Sure.
So that question first, and I'll get to you.
Okay, so obviously no one in the room needs to be convinced that formal methods are good, but I'm curious empirically with the handwritten implementations that you've replaced, what have the failure modes been? Has it been like the algorithm wasn't implemented correctly? If for GMP, was it like memory safety issues? Like what actually gets, what have the prior problems been?
Yeah.
define instruction as fixes.
For the kind of code we're looking at, wasn't typically memory safety issues because it's such simple straight line code, but there are definitely cases of bugs that involved over 1,000 lines of code. Oops, I wrote the wrong register at this point in my assembly code. We have an appendix in our paper that classifies the kinds of bugs, and maybe like a quarter of them were at the abstraction level that we're directly addressing with this project.
Cool, thank you.
Sure.
I believe that one of the reasons why the ED255 format is famous is in the SYND instructions. So did you integrate this SYND instruction in your grammar, or trying to do that?
We have a little bit of that in the last extension that I'll talk about here. All right, sounds like I should go on these extensions. So there was a nice question setting up just how pleasant is it to use the reduction engine of a proof assistant to generate efficient code. It's not a perfect match with the conditions that would be relevant. So indeed, we faced some pain making that work and decided to build our own alternative. So what were the issues that we ran into? Well, some reasonable compiler inputs would actually leave the compiler to timeout. It would run overnight and use obscene amounts of memory. And we actually had to write all our code in continuation passing style in the first place to get it to work on any of these cases. And that was no fun, because we're not just writing it, we have to prove it. It's just a continuing tax on how much fun it is to develop new algorithms. So instead of trying to plead with Coq to do all these things right, we decided to build our own alternative, and that kind of appears as a new tactic. And we'd like to make this work so that you can imagine a future proof assistant that doesn't have fancy reduction heuristics in its kernel, but only knows how to do full reduction in the style of an interpreter. That would reduce the trusted base for the proof assistant, which is a nice benefit. And also we want this to work in a way where that's completely compatible with extracting a standalone compiler as a result of this process. We don't want to require the users of the compiler to be starting the call process and running the reduction engine of Coq. That's how the first release of this worked. But we want to be able to produce a more traditional extractive compiler. The way we do that is using a storied technique called proof by reflection, where we demonstrate a new tactic that takes in a list of proved rewrite rules, equalities with quantifiers, and a term we want to reduce with respect to both normal length calculus, reduction, and the rewrite rules. And produces a new term with a separately checkable proof of equality with the original. The way this works is the rules come into our tactic, they get reified as syntax trees in logic. Then we give them as a parameter to a generic reducer, which is a functional program in the logic. We write it once, and we prove it once. Then we reduce the reducer. I think my former student described this project sometimes as involving a compiler, or something like that. So here's one of those steps. Let's reduce the reducer. And this is using the normal reduction of Coq, but performance doesn't matter here because this step happens so infrequently. And then we take in the term we want to simplify and reify that, feed it into the specialized reducer, get out the syntax tree of the reduced term, and then basically run an interpreter on that to get back out the final term that we're looking for. So crucially, all the steps of here generate proofs so that they compose to produce this one equality proof. You can check without trusting anything about what we built here. There's no Camel plugin that does the reification, I think, which doesn't need to be trusted for the usual reasons that proof by reflection doesn't require trusting reification. So what's going on inside that box? Well, let's say I put these two rewrite rules in there about piano arithmetic. We compile them to ML style code that pattern matches on a term and figures out which rule should be applied at the top level of the tree. And we do that using Rupicola Architecture's algorithm for compiling pattern matching into decision trees. And then we have a verified decision tree execution engine, which itself gets partially evaluated with respect to a function like this one. So now we don't need to trust Camel's compilation of pattern matching because we're doing a verified version of it inside Coq. And by the way, this reducer needs to be written in continuation passing style, which used to be the case for all of our arithmetic routines, but now we push that just into this very meta machinery. We don't have to worry about it for an individual cryptographic algorithm. And the engine in the center of things is normalization by evaluation, which is a classic technique for bootstrapping on one functional language to build a reducer for another. So I won't give too much detail here, but we have a kind of weird denotational semantics that has some syntax left in it, which lets us use the execution of the meta language to build a simplifying interpreter for the object language. And there are these two classic reify and reflect type index functions that do the two directions of this. And naturally, just writing things this way can build you a lambda term reducer without having to explicitly think about many of the usual concerns of a reducer. And all we do to this standard recipe is we add a call to our pattern matching code down the plate right through an arrowhead that sees which rewrite rules are appropriate at that point. And so that user rewrite rules get interleaved with the standard steps of normalization by evaluation. So this function is written and type jack improved once in call. We also use an encoding called parametric higher order abstract syntax as the way that we represent lambda terms in binding. I'm not going to take the time to go into the details of this one. It uses polymorphism in a nice way to avoid indefinite terms. And given this encoding, I can then rewrite the code I showed. It looks almost the same as before, but now this is modulo the fact I'm using like LaTeX syntax instead of ASCII syntax. This really is accepted, parsed, type checked, and provable in Calc. The Calc implementation is convinced of termination, which isn't trivial for this kind of code in general, but just works out well using this kind of encoding. And so then we're completely reusing the meta language's variable context management, which the OCaml implementers have worked hard to make fast. And so we inherit that to get fast variable context management for our domain-specific compiler. And we can still prove it. And one other twist I didn't talk about yet has to do with an example you might want like this one, where I'm mapping over a list of numbers. The function I'm applying to each number includes a let binding. And what I want to do is lift all those let bindings for the different list elements up to the top, though some of them disappear because those cases get optimized enough. So this is an interesting interweaving of standard higher order program normalization with algebraic simplification. And so we want something like this to pop out for this program. With, like was mentioned in the question, some term sharing here to avoid blowing up the representation. The way we do that is using this classic tech theory idea of a telescope, a sequence of let binders with an expression in the middle. We actually target this telescope type with our general reducer. So we get this good behavior of lifting lets up to the top. And it's kind of like a monadic side effect that's threaded throughout the entire evaluation process. So those are the main, perhaps unusual aspects that wind up in this system. I think that's all I wanted to say about that piece. Any questions here before I move on? Yeah? I guess we need the mic to come.
Thanks. That's cool. What kind of equations do you pop into your generic magical thinking?
They're mostly arithmetic laws and laws about our favorite higher order functions. A mix of those is what lets us optimize well.
I might use math fusion.
Yeah, there are probably some examples like that. So we're freely using these higher order functions in the source programs in our arithmetic library, and there's arithmetic happening kind of at the leads of the computations. So those are the main places where we want to simplify things and get rid of all uses of higher order stuff.
Thanks.
All right. So connected to another question that came up, it's like I think people optimally in the audience, it was, hey, this is only straight line code. How can that be good enough for anything in the real world? Of course, there are other parts of cryptographic libraries that go beyond straight line code. So we want to be able to handle those too, still in the style of let's write nice functional programs and derive efficient low-level programs. So that forms the core of my former student Clement's PhD thesis that I can tell you about here. So we're probably all familiar with the classical logic where I want to verify a program with respect to a precondition and a postcondition. So we might throw a goal like this at an automated theorem prover that makes short work of proving it. But what if instead, I know my precondition, I don't know the program yet, but I know the postcondition is the result of the program should equal what some functional program outputs when given the input. And I'm going to search for a proof of this Hoare triple in a way where I'm filling in those question marks and learning the low-level program that matches the functional program as I go. So we can still throw this at a theorem prover, and we're going to learn the program as we go through filling in unification variables. As we're building what's going to be a separation logic derivation here to justify the low-level program that we found. So that's how the system works. It's an extensible separation logic prover that learns the programs that you want to verify as it searches for the proof. So our system is called Rupicola, which is the scientific name for the so-called caulk of the rock. And this system connects two systems, the caulk functional programs with our bedrock low-level language. So that's how that name came about. And so if we take a journey through this diagram, start at the top left. We write high-level specifications, as one typically does in caulk, to explain what correctness means for some program. Then you can use whatever your favorite proof-assistant technique is to connect that to a functional program that realizes its spec. And at this point, you apply our tool, Rupicola, to automatically translate your functional program down to a low-level program. In this case, in our language called Bedrock 2, which is sort of like C. It has good tooling for verification and verified compilation. And because we have that tooling, we can then, of course, compile to assembly code in a way that guarantees correctness with respect to the low-level program. So through that whole arc, we have related high-level specs down to the fast assembly code that comes out at the end. So as an example of invoking this tool, we might start with a functional program like this one, which uses a higher order function, entity ranged for all, to describe a kind of loop. And you can see there are operations like list array.get, where we're using suggestive type synonyms for classic functional programming structures like lists, so that we can see what imperative structure is lurking inside this functional program. And we've got some bitwise operations on bit vector types encoded in the functional programming language of caulk. So if you look at this, not too non-obviously, you can see C program struggling to get out there. So run our tool, and you get that C program. This is actually the variant of the syntax that we embed inside of caulk. So caulk will also parse this syntax for low-level code. And the process that generates it produces not just this code, but also a separately checkable proof that it has the same behavior as this function through a suitable isomorphism of the kinds of states you have at low and high level. And the process that does this is a lot like we're used to in interactive theorem proving, where we say build libraries of lemmas and register them as hints, or we build custom tactics that have domain-specific decision procedures. You can do all of that in this setting. Rupicola is extensible with new hints and heuristics of that kind, which are now not just proving facts, they're also figuring out the program at the same time as proving its correctness. So we can drop in some hints, and suddenly the compiler understands new patterns of functional code that should be mapped to just the right pattern of C code to get good performance. And that's everything I wanted to say about this extension. I have one more to go. Any questions here before I move on? Yes.
Can you leave some of this functionality back into caulk for like proof synthesis and stuff like that? Or was it just super limited to these C programs in general?
I don't think we're trying to innovate in general theorem proving, where you know what the theorem is. Do you have a more specific idea of where this might go?
Coming from the other computers where you really want to generate the proof terms because it's
So all caulk proofs generate proof terms, so I'm not sure what the delta would be.
well, I'm just wondering whether you actually innovated something here, it was all just trial and tested techniques that you took from caulk into this programming, or whether you found something new inside.
Well, it's different in the sense of figuring out programs, but I can't think of anything that you'd want to port to a setting of just here's a theorem, prove it for me.
Okay.
There might be something, just a note occurred to us here.
Thanks.
All right, so the last part is going to try to close some of that gap with the performance of the best assembly code. We don't have a paper about this one yet, but we'll be giving a talk about it at the Real World Cryptography Conference, which is a pretty different scene than Powell. So remember, there's about a factor of 2 difference in the running time of our generated C code versus the best assembly code. So we hooked up with some collaborators centered at the University of Adelaide, including Professor Yuval Liron, who are experts on low-level cryptographic implementation and security like time side channels and so forth. And they built this box over here that uses genetic search to try to find faster assembly code variants. And so code that comes out of our compiler at the abstraction level of really flat C code flows into CryptOpt, and it just goes into a loop of using heuristics to produce an initial assembly version of your straight line C line code, and keep trying different mutations and comparing them with each other by actually benchmarking them on real hardware. So you can get a cluster running, producing the fastest code for, in our case, I think 8 different variants of x86 processors. And it gets in a loop trying all these different versions, and in the end produces the x86 assembly that it likes best. And then it feeds back into an extension we put in our verified compiler, where first you're going to run it in the classic way to get out the C-line code to feed into this process. But then, to confirm the result that came out, you run it in a different way, whereas a new command line argument, you actually specify an assembly file. So the meaning is, check that this source program is functionally equivalent to this assembly program. The assembly can be produced using whatever heuristic approach you like, but because we added a formally verified equivalence checker into the compiler, you don't have to trust anything about the heuristics that are going into that generation of the assembly code. So let's dive into a little more detail on that equivalence checker. What we needed to include in it is a new semantics of just a handful of the x86 instructions that are relevant to this project. We didn't have to worry about most instructions. We had to build a simple symbolic execution engine for assembly and C-like programs that does limited modeling of pointers, just enough to handle the case of there's some arrays that are passed as input to a function, and you have to spill some of your local variables onto the stack. Those are the only cases where we're doing explicit memory access, so relatively simple symbolic execution handles them. So we need almost no kind of fancy reasoning about aliasing, for instance. No alias analysis needs to run on the code. We also built an SMT solver-inspired automated equality prover, which integrates arithmetic rewrites, sort of like the ones I was talking about in the context of our reduction engine, and similar to the ones that SMT solvers are good at applying. What we didn't need to do is build a full, complete theory of linear arithmetic or bit vectors like your typical SMT solver has. And while we use a data structure inspired by the egraph structure at the center of most SMT solvers, we didn't need to implement most of the features that make egraphs difficult, like where you need to merge equivalence classes of expressions after you create them because you learned some new fact. It doesn't turn out to be necessary for this setting, at least with the heuristics that we're using to generate assembly code. So all these features are now packaged up inside our compiler. You can access them by running it with an extra command line argument that says check that this assembly program is a correct match with the source program you started with. And we get pretty good performance results. This is comparing with what we were getting before, generating C code and compiling with Clang and GCC, and showing for each of these elliptic curves here, which are part of internet standards, seeing how much of a performance improvement we get versus what we used to see with off-the-shelf C compilers. And each of these performance improvements is averaged across 8 different variations of x86 processors from both Intel and AMD. And we see we can get some pretty big improvements, almost always, at least 50% of performance improvement, and in some cases, more than doubling the goodness of the performance. A few cases we actually see the code slow down a bit, but getting that close to optimal seems fine if you're especially paranoid.
Higher is better.
Higher is better, yeah.
Okay.
And what this graph doesn't show is that for the most recent generation of Intel processors that we included in this experiment, we actually did find new world champion assembly implementations, where presumably the standard compilers haven't yet adapted the new optimizations they would need to do this. So by doing brute force random mutation of programs, we're able to find those before that human effort has been put in and still connect it to the highest standards of correctness assurance by running our equivalence checker after the fact. All right, so that's all I got. Here's our GitHub URL. You can find the project. I'm happy to take more questions.
Thank you. Let's take a couple of more questions before.
Thank you for a great talk. So continuing my previous question, I've seen the instructions. So is your CryptOpt is going to discover the parallelism with the program and put them together in the single instruction?
That's a good question. I think you typically need to write your high-level code with those kinds of algorithms in mind. But then our equivalence checker does handle some SIMD instructions and is able to validate some compilations of those programs.
And question over. Have you tried using the equivalence checker to check equivalence between your code and handwritten expert code?
We've successfully checked a few of those, but we haven't been too thorough in scouring the web yet.
And can we have one last question? Anyone? Microphone will come.
Just curious, usually what's the time for a system like this, including you start with the spec until
Do you mean the compile time or in-the-field execution time of the generated code?
the compile time?
Yeah, so it's typically pretty fast. Some of the, especially the new reduction engine I mentioned, really sped up the compile time. I definitely do. I run this compiler sometimes in interactive demos. You can do a lot in a minute, which I think is, but even if it takes an hour, it is worthwhile in this domain. I don't remember the exact details across all these examples, though.
Thanks.
Very good. Okay, Adam, thank you.